This lecture deals with logarithmic differentiation, which is a variation or a place that we use implicit differentiation. So what is logarithmic differentiation? Well, it's as I just mentioned, it's a means of using implicit differentiation and logarithms to differentiate functions that are algebraically complicated or functions that are very unusual where the ordinary rules of differentiation don't apply. We don't have ways to deal with them. So as an example, if we had y is equal to, as you see here, the fraction square root of 1 minus x squared over x plus 1 to the power 2/3, we could use this, we can find the derivative of this, dy dx, by simply using the quotient rule and the various forms of the chain rule that would be needed. It would be messy, complicated, long process. Well, logarithmic differentiation can actually make that process easier. Now, another example, y equal x to the power x. We've never seen anything quite like this. We would know how to deal with y equal x to the 5th power or y equal to 5 to the x power, but nothing like x to the x power. So we don't have rules of differentiation that tell us how to deal with this, but logarithmic differentiation can unlock the key, can unlock the door to getting that done. Now, as an introduction to logarithmic differentiation, though, there are a couple of things that we need to remember before we get into the process. And the first is, how do we take the derivative of the natural log of an expression? So in this example, or in this statement, we're assuming u is some expression in x. It might be x squared plus 1, it might be 2x. We don't really know what it is. But nevertheless, we can find the derivative by saying 1 over the argument, so that's 1 over u, times the derivative of u. And we learned that a while back, so we ought to be familiar with this. So it doesn't really matter whether our argument's called u or some other variable y. Again, we're just assuming that y is a function of x here. If this variable does not match x, then we have to use the chain rule, which says it's going to be 1 over the argument y times the derivative of y. And that's what's stated here. Now, next, I'd like to remind you of the 3 laws of logarithms, called the product law, the quotient law, and the power law. And I'm sure you remember these, but it's good to be reminded. The logarithm of a product of 2 quantities, a and b, is the sum of the logarithms of each of those quantities. So a and b might be numbers, they might be variables, or they might be variable expressions. As long as we're taking the logarithm of a product, then we can write that as the sum of the logarithm of each of the factors. In a similar fashion, the logarithm of a quotient, logarithm of a over b, is equal to the logarithm of the numerator minus the logarithm of the denominator. And the numerator and denominator may be complicated expressions. And lastly, in the power rule, if we have the logarithm of an expression to a power, we can write the power as a coefficient. We say we can bring the power down, so we can write that power times the logarithm of the expression to the first power. All of these laws assume that each one of the appropriate logarithms involved is defined. Now, sometimes, I'm sure you remember these also, there's some things that we cannot do. There are mistakes that are commonly made, but we cannot do them. For instance, if we have the logarithm of a sum, the logarithm of a plus b, well, we don't write that as the logarithm of the first plus the logarithm of the second. We do not have a way of dealing with that expression. That's as simple as we can write it. So don't go about trying to say that it's equal to this, because it's not. In a similar by the way, logarithm of a plus logarithm of b is the logarithm of the product, not the sum. Now, in a similar fashion, whether it's the sum, a logarithm of sum, or the logarithm of a difference, we cannot distribute that logarithm. We cannot break down a logarithm of a difference. We don't know how to deal with this. So if we run across the logarithm of a difference, that's as simple as we can write it. We cannot break it down further. Now, We've already stated what the logarithm of product is. It's over here. The logarithm of product is the sum of the logarithms. So don't go about saying that the logarithm of a times b is the logarithm of a times the logarithm of b. We know how to deal with this, but it's not this fashion. We don't deal with it by writing that. We deal with it by saying, oh, it's the sum of logarithms. And likewise, the logarithm of a quotient is not the logarithm of the numerator divided by the logarithm of the denominator. What is it? It's the logarithm of the numerator minus the logarithm of the denominator. So we cannot write that. If we see a logarithm of a quotient, oh yes, that's the difference of logarithms. So be careful, please. Okay, our first problem is stated, use logarithmic differentiation to find f prime of x if f of x is x times the square root of x plus 1. We'll break down the steps and then we'll summarize the steps when we're finished. So if you are to find the derivative of a function and it's written in functional notation as it is here, the very first step is to change it to y notation, to eliminate the function notation, because we're going to need to manipulate these terms quite a bit. Now, the second step is to take the logarithm, the natural logarithm of both sides of this equation, or this statement. So we'll take the natural log of the left side, so that's the natural log of y, and that's equal to the natural log of the right side. So the natural log of x times the square root of x squared plus 1. Now the third step is to use the three laws of logarithms and any other algebraic techniques to simplify the right-hand side. The left-hand side is always going to be the natural log of y. So what we recall about the laws of logarithms, if we have the logarithm of a product, and we do, x times the square root, that can be written as the logarithm of the first factor, x, plus the logarithm of the second factor, which is the square root of x squared plus 1. Now, we can still simplify further using laws of logarithms, because after all, the square root of x squared plus 1 can be written as x squared plus 1 to the power 1/2. And if we do that, then we can write, we can use the third law of logarithms, put the 1/2 in front of the natural log. So we'll take a further step and write this as the natural log of y is equal to the natural log of x plus 1/2 times the natural log of x squared plus 1. And that's a result of bringing the exponent off the square root down in front of the logarithm. As we said a while ago, though, we can't do anything further with this logarithm. No more rules, because this is a sum. And so we can't break this down any further. Now the fourth step in logarithmic differentiation is, once we've used all the rules of logarithms to simplify this right-hand side, is we find the derivative of both sides. So we take the derivative of both sides since each side is equal. So we have the derivative with respect to x of the natural log of y. And then that's equal to the derivative of this right side, which is two terms, and so we can write that as the derivative of the first term, which is just natural log of x, that is the derivative of the natural log of x, plus the derivative of the second term, which is a constant times a function. So that's the constant 1/2 times the derivative of the natural log of x squared plus 1. Now, actually, I've written down what we're going to do. Now let's actually perform these derivatives. Well, we saw earlier the derivative of the natural log of an expression other than x is 1 over the expression, so we get 1 over y, and then we have to say times the derivative of the expression, and so that's the derivative of y, of course, with respect to x. Now in this case, the argument is exactly x, and so the derivative of the natural log of x is just simply 1 over x. And in this case, we have our constant 1/2. Now, again, we have to use the chain rule because x squared plus 1 is not x. So it's 1 over the argument, that's 1 over the x squared plus 1, x squared plus 1 there, it's hard to read, times the derivative of the argument. But the derivative of x squared plus 1 is 2x. So that's the derivative of the argument. And then I think we can do a little bit of simplifying on the right-hand side before we go further. So let's make some room. So we have 1 over y times dy dx is equal to 1 over x. And let's see what we have here. We have this 1/2 times this 2x, which just leaves x, and so we'd have x times this fraction. So we end up with x in the numerator, and the denominator, of course, is x squared plus 1. That's simplifying this portion. Okay, the fifth step, I think in my summary I don't actually have 5 steps, but the fifth step is that what we're trying to do, let's not forget, we're trying to find dy dx, and there it is. But we need to get it alone. So we need to multiply both sides of this equation by y so that we just get dy dx. After all, y times 1 over y. So we're going to say, here's what we're doing. We're going to say y times this side is equal to y times this side. And what does that do? Well, on the left side, of course, that just leaves us with dy dx. So we're multiplying both sides by y. And so that leaves dy dx over here. Now, here's the extra part of the kick, is that we have to remember that we know what y is. See, y was our original function. It's hard to read that. Y originally was x times the square root of x squared plus 1. So what we're going to do is in this spot for y, we're going to write that x times the square root of x squared plus 1. And of course, that's all I've done is replaced my y value, and so that's times 1 over x in here plus x times x over x squared plus 1. Now, as we actually distribute that multiplier, now we're simply simplifying. That's what we're working on, and it takes a little bit of algebra here. Dy dx, well, what we're going to do is multiply this factor times 1 over x, and when we do, the x's will cancel, and so it leaves simply x square root of x squared plus 1. Now when we multiply this factor with this fraction, we'll get a numerator that is x squared, that's the x times the x, and we'll have the square root of x squared plus 1, and of course that's all divided by the x squared plus 1. And we'd probably take this a step further by thinking of, here's one more thing we can do algebraically. We can think of this square root as x squared plus 1 to the power 1/2. And so we have a power of 1/2 on top and a power of 1 on bottom. And so as we simplify that, we'd end up with a power of 1/2 on bottom. And so let's write that in here. We'll have dy dx, which is what we're looking for, is equal to the square root of x squared plus 1 plus x squared, and as we move this to the bottom, it's a minus 1/2 exponent and a 1/2 exponent together, which gives us a positive 1/2 exponent, which is the same as the square root. Now I suppose there's an argument that could be given that we might want to further simplify this result by adding these two expressions together. But I think for our purposes now, that's a different idea. Of course, we could get a common denominator and we could add those together. But I think for now I'll leave that alone. Okay, in summary of what we've just done, I've written the guidelines for logarithmic differentiation. First, we make sure that we replace any function notation with y notation, and then we take the natural logarithm of both sides. Once we've taken the natural logarithm of both sides, we simplify the right side as much as possible using the three laws of logarithms. After we've got the right side simplified as much as possible, then we find we take the derivative of both sides, and during that process on the left side we'll end up with the derivative of the natural log of y, which we remember is 1 over y times dy dx. So that's a critical part in our process. Now after we've taken the derivative of both sides and simplified, since the left side is 1 over y dy dx, and what we're looking for is dy dx, is we multiply both sides with y, leaving dy dx alone on the left, and then on the right we replace y with its original functional value. And we may do some algebraic simplification beyond that. Let's look at the next example. This looks like we don't really know how we might approach this. I suppose we could do this using a normal method, but the three factors make it a little bit difficult for us. So using logarithmic differentiation, first we take the logarithm of both sides. So we'll have on the left side the natural log of y, and on the right side the natural log, let's do this all at once. We have the natural log of a product of three things, so that's the sum of three things, and in each one of those has a power on it. So we could write this as 5 times the natural log of x minus 3 plus 3, that's this exponent, times the natural log of 2x plus 1 plus 7, that's this exponent, times the natural log of 5x minus 2. 5x minus 2. First we took the log of a product as the sum of logs, and then we moved the exponents down. We did that all in one step. So we have this right side simplified as much as possible using laws of logarithms, so we take the derivative of both sides. Let's see if we can just walk through this finding the derivative. Remember, we're going to find the derivative here of this side, the derivative here, the derivative here, and the derivative here. So the derivative of the natural log of y we saw is 1 over the argument times dy dx, so I'm just going to write that down. 1 over y times dy dx. The derivative of this, well, it's a constant times a function, so it's 5 times the derivative of this function. And of course, the derivative of a logarithm is 1 over the argument, so that's 1 over the x minus 3 times the derivative of the argument. Well, the derivative of x minus 3 is 1. Now likewise, a constant times a function, so it's the constant 3 times the derivative of the function. Well, the derivative of a logarithm is 1 over argument, so that's 1 over 2x plus 1, times the derivative of the argument. Well, the argument being 2x plus 1, that derivative is just 2. Plus the derivative here, well, the constant 7 times the derivative of the logarithm. Well, the derivative of the logarithm is 1 over the argument, so that's 1 over 5x minus 2, times the derivative of the argument. Well, derivative of 5x minus 2 is the constant 5. So we ought to be able to go in here and clean up this right side a little bit. We have 1 over y times dy dx is equal to, well, here this becomes 5 over x minus 3. Here 3 times 2 is 6, so it becomes 6 over 2x plus 1. And here 7 times 5, it becomes 35 over 5x minus 2. Now we multiply both sides by y, and when we multiply on the left by y, we're left with dy dx, which is what we're looking for. And then that's y times the sum of fractions. Oops, that's 35 over 5x minus 2. Now there's the next step we take is we replace y here with its original value or its original definition, and so that's this string of factors. So we have dy dx is equal to x minus 3 to the power 5 times 2x plus 1 to the power 3 times 5x minus 2 to the power 7 times this sum of fractions, 5 over x minus 3 plus 6 over 2x plus 1 plus 35 over 5x minus 2. Now there might be some question about whether we stop here or we continue to simplify. And I would, in this case particularly, I would suggest to you that we'll take a step of simplification. That is, we'll distribute this factor. We'll multiply this with each of these terms. Now when we multiply this with this first fraction, what we're going to have happen is an x minus 3 in the numerator cancel with an x minus 3 in the denominator. So it's going to be an x minus 3 to the 4th power left. And we'll still have this factor of 5 in the numerator. So it will be the original 5 that's here. And the x minus 3 to the 5th power will reduce to x minus 3 to the 4th power because that cancels. And then we have these other two factors. So 2x plus 1 to the power 3 times 5x minus 2 to the power 7. And then when we multiply all this with the second fraction, well, what's going to happen is the 2x plus 1 to the power 3 is going to cancel with this 2x plus 1 to the power 1 here. So that's going to change that to an exponent of 2. So we'll still have the 6, and we'll have the x minus 3 still to the 5th power because, to the 5th power because nothing canceled, but we'll have 2x plus 1 to the power 2 because this one of these powers canceled with the one down there. And we still have 5x minus 2 to the power 7. Well, let's see if I can squeeze this last term in. Now we're multiplying all this with the last fraction, and so, where have I gone wrong? This is supposed to be a 5x minus 2. I bet you caught me and I didn't. So that's a 5x minus 2 there. So the 5x minus 2 to the 7th power is going to reduce with the 5x minus 2 to the 1st power, and we'll still have the 35. And we'll still have the x minus 3 to the power 5. And we'll still have the 2x plus 1 to the power 3, but our 5x minus 2 is going to be to the power 6, isn't it? And that's about as much simplification as we could do. I suppose we could do some factoring at this point, but I think I'm going to leave it here and let you consider how we might factor out, what, an x minus 3 to the fourth power? That's hard to read. This should be an x minus 3 to the fifth power there, shouldn't it? We can factor out an x minus 3 to the fourth power. We can factor out a 2x plus 1 to the second power. We could factor out a 5x minus 2 to the sixth power and do a little more simplification. But we'll leave it here for now. Well, here's the problem that we discussed at the beginning of this lecture. An algebraically complicated problem that we can differentiate like we have so far using our normal rules. All of the problems we've done up to this point, we could use the normal rules, although a little bit difficult, of differentiation, and the same here. It would just be cumbersome. Logarithmic differentiation makes this something that we can deal with in a fairly routine manner. The algebra is still a little bit complicated, but let's go through this example. So this is written in terms of functional notation. So as you recall, the first thing we're to do is to write it in y notation. That is, simply replace f of x with y. So we go ahead and get that taken care of. Now, after we've rewritten the function notation as y notation, then we take the logarithm of both sides. So the logarithm of y on the left is equal to the logarithm of the ugly expression that's on the right. And of course that is an ugly expression. But the rules or the laws of logarithms let us simplify this left side significantly, because this is the logarithm of a quotient. And when we have the logarithm of a fraction, that's the logarithm of the numerator minus the logarithm of the denominator. So that's what I've shown here. The logarithm of the numerator minus the logarithm of the denominator. Now, of course, this numerator, the square root of 1 minus x squared, could be thought of as 1 minus x squared to the power 1/2. And of course here we have an expression to the power 2/3. And so we can use the third law of logarithms. Whoops. What's happened here? We can use the third law, sorry for that delay, the third law of logarithms to simplify this a little further. That is, the exponent that is on the 1 minus x squared, we can write as a factor in front. The exponent that's on the x plus 1 can be written in front. So now we have the logarithm of y pardon me, is equal to 1/2 times the logarithm of 1 minus x squared minus 2/3 times the logarithm of x plus 1. Now remember, these logarithms can't be simplified because we don't know how to deal with the logarithm of a difference or the logarithm of a sum. Okay, well, I think that's as much as we can use the laws of logarithms to simplify. So our next step is to take the derivative of both sides with respect to x. And that's the step that I've shown here. So we have the derivative of the natural log of y on the left. Now, here we have the derivative of this side, which is a difference, so it's the derivative of the first term minus the derivative of the second term. And of course, this being a constant, we can say 1/2 times the derivative of the logarithm, and minus 2/3 times the derivative of the logarithm. Let's get prepared here, look at a couple more steps. Now, on the left side, the derivative of the natural log of y with respect to x, remember, is 1 over the argument y, so 1 over y times the derivative of the argument, which is the dy dx. So the left side, and this is normal, this is what you see over and over, becomes 1 over y times dy dx. Now, over here, we have the constant 1/2, which I've rewritten, but we're taking the derivative of a logarithm, and the derivative of a logarithm is 1 over the argument. So we have 1 over 1 minus x squared, and then we have to multiply with the derivative of the argument. And so the derivative of 1 minus x squared is negative 2x, and that's what I've written here. Okay, I'm sorry. And of course here we have the constant 2/3 minus the 2/3 times the derivative of this logarithm. Well, the derivative of this logarithm is 1 over the argument, so there's our 1 over x plus 1 times the derivative of the argument, and the derivative of x plus 1 is just 1. So that's how we've written that. Now we'll go in and kind of clean up on the right side just a little bit. We still have the left side, which is 1 over y dy dx. Now on this right side, notice that we have this 1/2 and times a negative 2x, which will leave negative x in the numerator and 1 minus x squared in the denominator. So when we multiply all of this together, it simplifies to this fraction. And over here, of course, we have this 1, which doesn't bother us. We have the 2 times 1 in the numerator and 3 times the x plus 1 in the denominator. So there is our right side simplified. I suppose we could add or subtract in this case these two fractions, but I don't think that we need to be concerned with that at this point. So our next step is to multiply both sides by y. That leaves dy dx on the left side and y times the right side. There's y times the original right side. Now remember, after we get to this step, we replace our original y. Remember, y was just our function, and it was that complicated, the square root of 1 minus x squared over, what was it, x plus 1 to the power 2/3. And so we're going to replace our y value, our y, with this expression. So that's just y right there, our original y. And we might stop right here. I mean, now you're going to have to, that might be the end of the problem. That might be the way we leave our answer. You're going to have to take a hint from the answers that are left in the back of the book, or from the, if it's a multiple choice type question, whether this fits your answer or whether you need to simplify further. It might be worth your time. Not suggesting that you have to do this, but it might be worth your time seeing that one step further, if we went one step further and actually multiplied these, distributed this factor through this difference here, we could simplify to this stage. So see if you can figure out how we got that step. And of course we might go further from here. We might add those two fractions together. But I'm going to stop at this point. Well, as this says, now for the real power of logarithmic differentiation. In all of our examples previous to this, we've been able to find the derivative. We could have found the derivative using the techniques we've learned so far. But now we're going to be faced with a problem where we can't find the derivative using old techniques. But I'd like to take this time to kind of look back, see where we are, so that we understand these first two examples. We know how to find the derivative. Let's very first example, if y is x to the fifth, well, that's normal. We use what we call the power rule to find the derivative of y here. So of course we just know that that's 5 times x to the fourth power when we find the derivative. And we use the power rule when we have a variable to a power that is constant. So a variable to a constant power. Now in the second example, we have a constant to a power that's a variable. That's different. We do that differently. This is the situation where logarithms appear when we find the derivative. This is similar to y is equal to e to the x. And the derivative of e to the x is just e to the x. But now when our constant that's to a power is not e, but the constant 5, or some other constant, then it's that base to the same power, so 5 to the x, times the natural log of whatever the base is. So if that was e to the x, well, the natural log of e is just 1, so we'd end up with just e to the x. But it's a different process. We do not use the power rule when we have a constant to a variable power. We only use the power rule when we have a variable to a constant power. When we have a constant to a variable power, we deal with it differently. Now, the last example is completely different yet. It's a variable to a variable power. And to deal with this, a variable to a variable power, we must use, the only thing we have a hope of using is logarithmic differentiation. So let's look and see how we would find the derivative of x to the power x. So our function f of x is x to the power x, and we're to find f prime of x, or the derivative. So step 1, remember, of course, is to rewrite this in y terms. So we'll replace f of x with y, and so we have y is equal to x to the x power. Our second step is to take the natural logarithm of both sides, and so we have the natural logarithm of y is equal to the natural logarithm of x to the power x. Make sure that we understand what's happening. Now, the third step is to simplify the right side using laws of logarithms. And so here we have an expression to a power. We can bring that power down as a factor in front. So we'll rewrite this as the natural log of y is equal to the power x that was a power here, now as a factor, times simply just the natural log of x to the power 1. Now the third step is to take the derivative of both sides. The next step. So we take the derivative of the left side, derivative of natural log of y, and of course that's equal to the derivative of the right side, and the right side is x times natural log of x. Now we know the derivative of natural log of y with respect to x is 1 over y times dy dx. Get that done easily. Now here we're taking a derivative of a product. The first function x is x, the second function is natural log of x. So we say first function times derivative of second function. We're using the product rule, recognize that. So the product rule says first function times derivative of second function, and then we turn it around, plus second function, which is natural log of x, times derivative of the first function. And since the first function is x, it's the derivative of x. Well, of course, the left side is still 1 over y times dy dx. On the right side, we'll actually perform these derivatives. I just wrote down what we were going to do. So we have x, this x, times the derivative of natural log of x, which is just 1 over x. Of course, here we have natural log of x times the derivative of x with respect to x, which is just 1. And so we see on this simplification on the right side, we end up simply with, well, let's see, on the left side we have 1 over y times dy dx, and here we have simply 1, x times 1 over x is 1, and here we just have natural log of x. Whoops. Okay, so now we multiply both sides by y, and when we do, the left side is just dy dx, and the right side is y times the original right side, 1 plus natural log of x. But y is x to the x power, remember? That's what y is. And so as we finish this off, dy dx, which originally we were asked to find f prime of x, so we'll go ahead and say that f prime of x is y, x to the x power, times 1 plus the natural log of x. And I suppose we could distribute that, but I'm choosing to leave it as stated. So we'll leave our final answer in this form. That was fun, wasn't it? Okay, our next problem, imagine later in the month or on a test, simply says differentiate f of x is equal to 1 plus x to the power 1 over x. Now, we have to struggle all the time with what technique we're going to use. And let me point out to you the giveaway here that we're going to use logarithmic differentiation is the fact that we have a variable expression to a power that's a variable. So variable to variable power always requires, or usually requires, logarithmic differentiation. So once we've decided we're going to use logarithmic differentiation, then we recall that we need to rewrite it in y notation. So simply replace the f of x with y. After we've done that, we take the logarithm of both sides. So now we have the logarithm of the left side is equal to the logarithm of the right side. Then, of course, we remember that we then simplify the right side using laws of logarithms. So since we have the logarithm of an expression to a power, we can write the power as a factor in front of the logarithm using the third law of logarithms. So that's what I've done here. Bring the 1 over x down as a factor times natural log of the 1 plus x to the power 1. Now after we have that right side simplified, then we take the derivative of both sides with respect to x, and we have to use implicit differentiation. So the derivative of the left side is equal to the derivative of the right side. Now, I've emphasized the fact that the right side is actually a product. So when we go to find the derivative of this right side, we're going to have to use the product law of finding derivatives. Now, we know on the left side that the derivative natural log of y with respect to x is 1 over y times dy dx. So I've just simply written that out. And rather than doing everything in my head, I'm going to point out to you that on taking the derivative of the product, we use the product rule. And the product rule says we take the first function, which in this case is 1 over x, and we multiply it with the derivative of the second function. Well, there's the second function, and so I'm indicating that derivative here. Then we add to that just the opposite. That is, we take the second function alone and multiply it with the derivative of the first function. Well, the first function being 1 over x, and this is the derivative of 1 over x. Now, as we actually find the derivatives, let's see what's gone on here. The left side I've left alone. The right side I'm actually finding the derivative. So I have this 1 over x times the derivative of a logarithm. Well, to find the derivative of a logarithm, we say 1 over the argument. So there's my 1 over 1 plus x, and then we multiply with the derivative of the argument. Well, the derivative of 1 plus x is simply just 1, so that's where that 1 came from. Over here there's a little bit more involved. We have the logarithm times the derivative of 1 over x, and the derivative of 1 over x ends up being negative 1 over x squared, and let me remind you why. If we rewrite 1 over x as x to the power negative 1, then we find the derivative will have negative 1 times x to a power that is 1 less than negative 1. Well, of course, take that negative 1 and subtract 1, and we get negative 2. So we get negative, that's the negative 1, x to the power negative 2. And of course, x to the power negative 2 is 1 over x to the positive 2. And so that's how we ended up finding that derivative to be negative 1 over x squared. That was the derivative we just calculated. Okay, well, let's see if we can't do some simplification to this this right-hand side. See if we can't make it look a little bit better. I don't want to lose track of what y is. Okay. So on the right-hand side, the first term just simplifies to 1 times 1 over x times 1 plus x. And so I've written that here. And then on the right side, we have a positive times a negative, which becomes minus. And we have the natural log times 1 in the numerator, so that's just natural log of 1 plus x, and then only x squared in the denominator. So we have the right side simplified. Now we multiply both sides by y. Well, I'm sorry for the interruption here. It's going to require me, I apologize for the delay, it's going to require me to come all the way down. I don't know what I did, but it wasn't good. Okay, so we multiply both sides by y, leaving dy dx on the left, which is what we're looking for, and we have y times the original right side. And then remember, lastly, well, maybe not lastly, but in this case it is lastly. Lastly, we replace y with its value. And remember, the original function was f of x is equal to 1 plus x to the power 1 over x. So this becomes our y, and then times that right side. Now there's all kinds of arguments about what we might do next if we multiply that out, if we subtract these two fractions. And we may be required to do some algebra in the future. It might be some difficult algebra. But for this problem, we'll stop right here. This is the answer that we're looking for. The last example we're going to look at in this section is finding the derivative of y equals 7x times the cosine of x raised to the power x over 2. Now, as we discussed earlier, we know we're working on logarithmic differentiation examples, but if we were faced with a problem like this outside of this section, like on an exam, like on a quiz, the giveaway, when we're analyzing what we need to do, we recognize that we have a variable expression to a variable power. And whenever that happens and we're finding the derivative, we need to make sure that we use logarithmic differentiation. So let's get started. I've just rewritten the problem, and I'm emphasizing the point that the power x over 2 is on the cosine of x, not on x itself. So we take the logarithm of both sides. And here I'm emphasizing that on the right side we have 7x times the cosine to a power. So when we actually have the logarithm of a product where the first factor is 7x and the second factor is cosine of x to this power x over 2. Of course, what we do next is simplify the right side using the laws of logarithms. And since we have the logarithm of a product, we use the first law of logarithms that says the logarithm of a product is the sum of the two logarithms. And so I've written the right side as the logarithm of 7x plus the logarithm of this cosine to a power. Now, when I have an expression to a power, logarithm of an expression to a power, I can use the third law of logarithms to bring the power down as a factor in front of the logarithm. So I've written the power x over 2 times the logarithm of the cosine of x to the first power. So I actually did a couple of steps in that one line. Now, The next thing, of course, is we take the derivative of both sides once we've simplified the right side. And rather than performing the derivative process, I'm showing taking the derivative of each side. So the derivative of the left side, of course, and the derivative of the right side, which is a sum. And so that's the derivative of the first logarithm plus the derivative of the second logarithm. Now I've emphasized here in this second term, the derivative is of x over 2 times. I put that red times sign in there to recognize that we have a product that we're taking the derivative of. And so to calculate this derivative will require that we use the product rule for derivatives, which I've begun on the next step. Now, there's a couple of things. Let's just go through here one side at a time and one term at a time. If we look above, we had the derivative of natural log of y, and we know that that calculates as 1 over y times the derivative of y with respect to x. So I've just rewritten that. Now when we look at the derivative of the natural log of 7x, remember how we take the derivative of a logarithm. It's 1 over the argument. So we have 1 over 7x, and then we multiply with the derivative of the argument. And since the derivative of 7x is 7, I've written that here. And we already know we're going to simplify on this the next step. Now, in this case, notice I've got these green parentheses. That's to emphasize that the derivative that we're looking at right here, we have to use the product rule. And so there's two terms. Now, when we have the derivative of a product, we say first factor, first function, that's x over 2, times derivative of second. So it's times derivative of natural log of cosine x. And then plus. And then we do the opposite. Second function, which is natural log of cosine x, that's written here, times derivative of first function. So times derivative of x over 2. Now I highlighted this because clearly I didn't write x over 2. And I recognize that if I write x over 2 as 1/2 times x, that's an easy derivative to calculate. If I leave it as x over 2, I might think I need to use the quotient rule. So I've written x over 2 as 1/2 x, and that's what I'm taking the derivative of. Now, in the next step, in the next line, I'm going to go through and simplify here. I'm going to calculate this derivative and calculate this derivative and rewrite a little bit. So let's see that next line. So the left side hasn't changed any. Still 1 over y times dy dx. This first term, 1 over 7x times 7, clearly simplifies to 1 over x, and that's what I've written here. Now, inside these green parentheses, I've eliminated the green parentheses, but inside these green parentheses, I have x over 2, there's my x over 2, times the derivative of the natural log of cosine x. Oh, I have to use the chain rule. The derivative of natural log is 1 over argument. So I have 1 over cosine of x times the derivative of the argument. Well, the derivative of cosine of x is negative sine x, so I've written that here. So this derivative is written in this space. Plus, here's my plus. Now I'd have natural log of cosine of x times derivative of 1/2 x. Well, derivative of 1/2 x is just 1/2, so I've written the 1/2 in front of this natural log of cosine x. So that's what my next line looks like. And I've calculated all the derivatives, and so now we might see if we can simplify and make this look a little bit different. Now, it takes practice, and certainly something that we always want to look for. I'm noticing here that 1 over x I can't simplify, but look at this product. Here I have a positive times a negative, which will be negative. So that's why this negative sign appears right here. And then I notice when I multiply these two together, I'll end up with sine of x over cosine of x. Oh, well, sine of x over cosine of x is tangent of x. So this becomes minus x over 2 times tangent of x. and then plus this last term, 1/2 times natural log of cosine of x. Remember, this is our original function. We'll need to know what y is in a few moments, won't we? Because we're going to multiply both sides by y. Okay, in fact, that's what we do next. We're trying to solve for dy dx. Don't ever lose track of that. We're asked to find dy dx, and there it is. So we need to get it alone, and the way we do that is we multiply this left side by y. So we'd get 1 instead of 1 over y. But if we multiply the left side by y, we have to multiply the right side by y. So that's why that y is appearing there. And it's y times this entire side. And then, as we just mentioned, we really know y. Y is the original function. So we replace this y with its value, which is all of this. So here's y times that right side that we had. And most likely I would leave my answer like this. Clearly we could multiply this out, we could add and subtract fractions. There's a lot of things that we could do, but I don't know that any one of them would be a better expression than what we have now. So this is what we're happy with. This is the final answer. Well, remember, you can go back with any of these examples and you can go through it more slowly, you can pause it, you can rewind it, you can look at each step, and you can see if you can replicate what we've done in these examples. Remember how we do it, and remember the circumstances in which we have to use logarithmic differentiation.